So the next thing we're going to talk about are the gas laws. And the gas laws that we're going to look at pertain to gases in an ideal state. So these aren't the gases that you are familiar with and you have seen, let's say, in like party balloons or anything. These are fictional gases that we've made fictional to kind of help with calculations and our understanding. And so the assumptions that we make for ideal gases are that these fictional gases do not attract or repel one another. And the second one is that gas molecules have no volume. These are actually going to be derived from a bigger kinetic molecular theory of gases that we'll talk about at the end of this video. But these are just the two assumptions we really want to focus on for the ideal gas law. So when we take these into consideration, we can use a formula that talks about ideal gases. And the formula is called, or is just, PV equals nRT. Now this law is actually derived from a few different people, but because you have most likely, hopefully, taken general chemistry before you came and decided to take your PCAT, this is the first one we're going to start with, and then we'll kind of break it down and go into Charles, Boyle's, and the rest. So there are 5 variables for the ideal gas law, and we'll just talk about each variable, the units you need to know, and what each one really represents. So we'll talk about R last for a specific reason, but the first one will just be the variable P, and P is just for pressure, which should be in atmospheres. Now, you have to know atmospheres, and it would also be good to know how to convert 2 atmospheres from millimeters mercury. So 760 millimeters mercury is equal to 1 atmosphere of pressure. And a lot of times you might see some kind of equation where it asks for some variable, but you're given 780 millimeters mercury. Just divide 780 by 760, and you'll find out your real pressure in atmospheres. So the next one is volume. This should always be in liters. Most likely, you won't have to worry about any kind of conversions there besides milliliters. N is moles. Be careful because moles can be further broken down into grams over molar mass. And I'll use a lowercase m for mass. Molar mass will just be a capital M when we do calculations. Last, or second to last technically because we haven't done R yet, we have T. T is temperature. And temperature can be, or it has to be, in Kelvin. That's another one that you should be really careful about because they like to give you Celsius. So if you get Celsius, your temperature in Celsius plus 273 is going to be your degrees Kelvin. Now, why did I leave R last? So R is just the universal gas constant, and a lot of people get kind of mixed up between whether this gas constant is 8.314 or 0.0821. Now, let's talk about the one that you'll most likely see first, 0.0821. The units for the 0.0821 is just going to be atmospheres liters over moles Kelvin, which kind of makes sense because that is going to balance out all of the other variables. Whoops, I'm not going to balance out myself. If I multiply temperature, or like Kelvin by Kelvin, I cancel out. If I divide by volume, I cancel out, yada yada. The other way that this could go is 8.314. And we are going to see 8.314 and only one specific occurrence. Everything else is the same, so I'll actually just copy and paste this so that gets busy. Almost. You know what? We'll just drag that all the way out here. The only thing that's different here is instead of atmospheres, we will just have kilopascals. And that's why you probably won't have to use this very often, just because you won't really deal with kilopascals very often at all for your exam. Just focus on 0.0821 and then make sure pressures in atmospheres, volumes in liters, and temperatures in Kelvin. So from the ideal gas law, there are a few things we're going to need to know how to derive. And those three things are grams, molar mass, and density. These three are the ones that you can't easily get straight from the ideal gas law. It's not one of the variables automatically given to you. So these three, you just have to put in a little bit of work into the derivation behind it, but it should be pretty simple to derive, so I wouldn't go about memorizing these formulas. So the first one is going to be grams. And so from PV equals nRT, how do we get grams? So the first thing you can do, and there are multiple different algebraic ways to go about this, is I can take both sides and just divide by RT. And that will give me PV over RT is equal to N. Now, N is equal to the mass over molar mass. So PV over RT is equal to lowercase m for mass over capital M for molar mass. So now I can just divide both sides by capital M for molar mass. And that will give me PV molar mass over RT is equal to grams. So there's the first derivation. Now for molar mass.
I'm so sorry.
Bless you. Think I'm going to cut for that, huh?
Just right now.
Nah.
Okay.
It's in the final.
Oh,
PV.
Please write it down.
No, never.
Okay.
PV equals nRT, and I hope they have their headphones in too, so it just really gets to them.
Oh.
PV equals nRT. So from here, we'll do the same exact step. I will just divide by RT. Wow, look at me shortcutting this. Now we have PV over RT is equal to N. N is, of course, equal to grams over molar mass. And now we have the flipped issue, which is we don't want this variable by itself, we want this variable. So I could just take the inverse of both of these, but I'll do the long way. So the long way involves me first multiplying both sides look at me just flipping colors, by M, that will give me PV, let's work this up a little bit, PVM over RT is equal to lowercase m. I'll multiply both sides by RT. Now I have PVM is equal to MRT. Lastly, divide both sides by PV. And I will have my molar mass is equal to MRT over PV. So now, density. Density is going to be grams over volume. And in this case, we'll do MV for density. So let's start this again. PV equals nRT. If I want to isolate V on top of my grams, I should probably just start, we'll wing it. So we'll take RT, divide both sides. Now I have PV over RT is equal to N. I feel like I could have just done so much other stuff, but hey, PV over RT is equal to mass over molar mass. And now, how are we going to isolate this? We'll just multiply both sides by capital M. Now we have PVM over RT is equal to lowercase m. And lastly, by dividing both sides by V, I have mass over volume is equal to pressure times the molar mass over RT. So there are the three derivations. Now let's move into practice problems. What is the volume that 43 grams of NH3 gas occupies at STP? So do we have any conversions we need to make? Yes, because in PV equals nRT. We also should say we're assuming ideal conditions here. In PV equals nRT, we have moles, but we don't actually have the number of moles of NH3. But I know that moles are equal to grams over molar mass. And if I have 43 grams, and I know that the molar mass of NH3 is 17 just because 14 for nitrogen, 3 for hydrogen. I have 2.53 moles of NH3 gas. And now, what else do I need? Well, PV equals nRT. I'm looking for the volume, but for temperature and pressure, you should note that this says we are at STP. So STP just means standard temperature and pressure. So it's kind of like these are constants. At STP, the temperature is 273 degrees Kelvin. The pressure is 1 atmosphere. Sure. So now we know the moles, we know the temperature, gas constant is constant. Pressure we know, we can find the volume pretty easily. So 1 times the unknown volume is equal to 2.53 times 0.0821, because this is in atmospheres, times 273. So 56.7. This gas will occupy 56.7 liters. Let's highlight that. All right. Moving on. At 800 millimeters mercury and 298 degrees Kelvin, a gas occupies 35 liters of space. How many moles of this gas are present? Great. Any conversions we need to do? Pressure is not in atmospheres, and 1 atmosphere is equal to 760 millimeters mercury. So 800 divided by 760 roughly 1.05 atmospheres of pressure. So with that given, basically we have everything we need. Pressure is 1.05. This occupies 35 liters of space. We are looking for moles, gas constant, and then 298 degrees Kelvin. .5. We have 1.5 moles of this gas. C, 26.8 grams of a diatomic gas. So diatomic just means that in the natural state, this gas is composed of 2 molecules bound together, or 2 elements bound together. So examples of that could be H2, N2, O2. All of these are gases that exist in a diatomic state. An example of a monoatomic would just be helium. Helium doesn't form He2. So we know we have 26.8 grams. We have got an 8-liter container of fixed volume. So it's going to stay at 8 no matter what. At 30 degrees Celsius, the gas exerts a pressure of 3 atmospheres. So we have pressure is equal to 3 atmospheres. At 30 degrees Celsius, so this isn't in Kelvin, but the temperature will just be 30 degrees Celsius plus the conversion factor, 273, means that our temperature is 303 degrees Kelvin. Now, what are we asked to find? The identity of the gas. So how am I going to find the identity? Well, the only thing that can really tell us about the identity of this gas is going to be the molar mass. And if I'm a diatomic gas, that means that the molar mass that I find is going to be double the element's atomic mass. So if I set this up, PV equals nRT, 3, 8, I don't know N, R is a given, and then T is 303. So let's just get all of that balanced out. So it'll just be 24 divided by 24.8763. Yeah, that's right. this means that 0.9647 is equivalent to the number of moles that we have. And our moles are going to be 26.8 over the molar mass. I'm switching here between molar mass by representing it with two uppercase M's. I'm sorry. I'll probably not do that unless I've already done it a bunch. I don't think I have. This is just equivalent to 0.96477. M equals 26.8. Dividing 26.8 by 0.96477 is 27.8. So this is the diatomic mass. So because this is diatomic, there's two of the same elements here. So this would be roughly equal to 14. And which element weighs roughly 14? Nitrogen. So this is likely nitrogen gas. What is the density of a solution of H2S at 500 millimeters mercury and 400 degrees Kelvin? Wow, that's fun. All right. So let's actually travel back up here real fast. We found that our density was PM over RT. So PM over RT is equal to mass over volume. So what is our mass? Well, actually, it doesn't matter. This is all density. So we're trying to find density. Don't really have to worry about anything. All we care about is the pressure, molar mass, R constant, and T. So that'll just be, what's H2S? Roughly 32 plus 2, so 34. So 34 for our molar mass. The pressure is 500 millimeters mercury. Need that in atmospheres. .66. Divided by 0.0821 and 400 degrees Kelvin. .68 is equal to our density. So we've just been talking a bit about the ideal gas law, and we originally said that it was the product of a few different gas laws by individual people. Now, we're going to go a little bit into those in just a shorthand approach, but the first is Boyle's law. And Boyle's law just says if you don't change the temperature, the pressure and volume of an ideal gas are inversely proportional. I should also say, it's probably good if you correlate P1V1 to P2V2, just because a lot of the times you could be asked, whose gas law is this? You'll have to give that kind of answer. So for Boyle's law, this kind of makes sense that if we don't change the temperature, the pressure and volume are inversely proportional, just because PV equals nRT. The ideal gas law states that we have a non-changing amount of the gas, so moles are constant. The universal gas constant is constant, and then the temperature here doesn't change, so that's also constant. So the properties of this ideal gas are going to directly just depend on the pressure and volume. So that means that the pressure and volume before whatever they equal will also be equal to the new pressure and volume. So if I say that the original pressure, as an example, was 2, and then the original volume was 4, the pressure and volume of this gas would equal 8. Now, given that that pressure and volume equals 8, what happens if I increase the pressure to, let's say, 8? Well, now the new pressure is 8. The volume is unknown, but it still has to be constant at a total pressure volume of 8. So volume would just go down to 1. And so here, by increasing the pressure, I decrease the volume. And you can see that here. So that's Boyle's law. And for example 8e, an ideal gas at 1 atmosphere was expanded to 3 times the initial volume without changing the temperature. What is the new pressure? So P1V1 equals P2V2. An ideal gas at 1 atmosphere was expanded to 3 times the initial volume. So I don't know the original volume. I don't know the final volume, but I know the conversion factor. So if I increase the volume threefold, I need to decrease the pressure threefold to balance this out. So the new pressure, P2, will be 1/3. P2 equals 1/3 P1. And so that's how we're going to make it inversely proportional. Now we get into Charles' law. At constant pressure, the volume and temperature of a balloon are directly proportional. So let's say again, let's just give an example here where let's give a really low temperature. And so let's say we have 10 degrees Kelvin, and then we have a volume of 1 liter. That's insane, but that would just be equal to 0.1. So now, if I want to increase the volume and I change that to 5, 0.1 is equal to 5 over T. Well, now my temperature needs to be 50, so that 5 divided by 50 equals 0.1. So as I increase my volume, I also increase my temperature. At constant pressure, a balloon containing an ideal gas was found to occupy 50 liters of space at 298 degrees Kelvin. So 50 liters. Is my handwriting just going more and more downhill? At 298. At what temperature would this balloon take up 60 liters of space? So 60 over T2. So, however you really want to do this math, this looks confusing. Let's just change that. There, that looks better. I'll just multiply both sides by T2. Now we have 50 T2 over 298 is equal to 60. Multiplying both sides by 298, T2 is equal to 1,700 and 880. Now, dividing both sides by 50, we have 357.6. So the new temperature to account for this expansion would have to be 357.6 degrees Kelvin, and that is T2. Now we get to Avogadro's. So at standard temperature and pressure, so at STP, 1 mole of any gas will occupy, and this is a rule here, 22.4. I'm going to spend the time to write this as pretty as possible. If you can't read that, that's on you. In the reaction below, HCl is made when I react 5 moles of H2 gas with 5 moles of Cl2 gas at STP. What volume in liters will the HCl gas occupy? All right. So this is bringing in a number of things now. So first of all, I should ask myself just automatically, is this equation balanced? Well, I have 2 hydrogens and 2 Cl making 2 hydrogens and 2 Cl. So I'm good there, no tricks. And it says HCl is made when I react 5 moles of H2 gas. So I'm having 5 of these with 5 moles of Cl2 gas. So 5 of those. And I can see that when I use 1 mole of H2 and 1 mole of Cl2, I make 2 moles of HCl. So if I'm using 5 of H2 and 5 of Cl2, I would expect to make 10 moles of HCl. So now, if I know that 1 mole of a gas will occupy 22.4 liters of space, 10 moles will occupy 10 times that. So 224 liters of space. Option A.